Your phone says 10:42. So does your computer. The departure board agrees. The navigation screen agrees. Even the clock on the wall is close enough that nobody questions it. But none of those clocks actually knows what time it is. Each one contains a local oscillator, a tiny mechanism that continues counting after the last correction. It can run fast. It can run slow. Temperature can change it. Age can change it. Power loss can stop it entirely. And yet billions of clocks remain synchronized closely enough to coordinate trains, power grids, financial markets, telecommunications, satellites, and nearly every computer network on Earth. So who tells your clock what time it is? The answer is not one perfect atomic clock hidden in a government vault. It's a chain of natural cycles, ancient divisions, mechanical inventions, railroad agreements, laws, atomic measurements, international institutions, satellites, servers, and software. A system built over thousands of years to make separate clocks agree. Before anyone could ask what time it was, people could already see that time was passing. Daylight returned after darkness. The moon changed shape and returned to the same phase. Seasons altered the length of the day, the height of the sun, and the behavior of plants and animals. Stars rose, crossed the sky, and returned in familiar patterns. These cycles were dependable enough to organize life. People could gather at dawn, travel while the sun was high, return before darkness, and measure longer intervals by moons, seasons, floods, harvests, and migrations. But nature did not supply a clock face. A sunrise did not arrive with a numeral attached to it. The moon did not label its phases. The seasons did not divide themselves into equal boxes. Nature provided repetition. Humans supplied the divisions. That distinction matters because nearly everything we now call time is built from two different layers. The first is physical: rotation, orbit, vibration, decay, and repetition. The second is conventional: where we place the boundaries, what we call the units, and which clock we agree to follow. The hidden standard begins when those layers are joined. Today, an hour is always 60 minutes, but the earliest hours did not work that way. In many ancient systems, daylight was divided into 12 parts. Night could also be divided into 12 parts. The number of hours remained the same, but their length changed with the season. A long summer day produced 12 long daylight hours. A short winter day produced 12 short daylight hours. At a mid-latitude location, a 15-hour summer day would produce daylight hours 75 modern minutes long. A 9-hour winter day would produce daylight hours only 45 modern minutes long. Those numbers are only an illustration. The exact length depended on latitude and date. But the principle is the important part. The hour followed the sun. The system was not defective. It matched a society in which daylight itself shaped work, travel, worship, and public life. The problem appeared when people wanted a device to repeat the same interval throughout the day and through the year. A machine does not naturally stretch its tick in summer and compress it in winter. A machine prefers repetition. And once equal mechanical intervals became useful, the hour began to change from a seasonal division into a standardized unit. A clock needs energy. In an early mechanical clock, That energy might come from a descending weight. The weight turns a drum. The drum drives gears. The gears can reduce motion and transfer it toward a display or a bell. But gears alone don't make a clock. Without regulation, the mechanism simply runs. The essential breakthrough is the escapement. The gear train pushes against an escape wheel. A pallet locks that wheel, preventing continuous rotation. An oscillator moves the pallet, releases one tooth, receives a small sustaining impulse, and locks the next tooth. Lock, release, impulse. Then the cycle repeats. The oscillator determines when the gear train is allowed to advance. The escapement counts that repetition and transfers it towards the display. Continuous force becomes controlled steps. Early mechanical clocks were not precise by modern standards. Friction changed. Drive force changed. Temperature changed. The geometry was imperfect. But the machine could repeat intervals without looking at the sun. That separated timekeeping from immediate observation of the sky. Later oscillators improved the repetition. The Foliot gave way to the pendulum in many clocks. Portable clocks used balance wheels. Quartz crystals provided much more stable electronic oscillation. Atomic transitions eventually supplied a reproducible frequency reference. The technology changed. The basic job remained the same. Create a repeatable interval, count it, display the result. A well-regulated clock can be accurate and still disagree with another accurate clock. Before standard time, that was normal. Local noon occurs when the sun crosses a place's own meridian. A city farther east reaches local noon before a city farther west because Earth must rotate farther before the west meridian faces the sun. Consider Philadelphia and Pittsburgh. When the sun reaches Philadelphia's local meridian, a local clock there can read noon. At that same moment, Pittsburgh is still approaching its own local noon. Later, Pittsburgh reaches noon, while Philadelphia's clock has already advanced. The two clocks disagree because the cities occupy different longitudes. Neither clock is wrong. Earth rotates 360 degrees in roughly 24 hours. That gives a useful conversion. 15 degrees of longitude corresponds to 1 hour of solar time. 1 degree corresponds to about 4 minutes. Move west, and local noon arrives later. Before time zones, local time changed continuously across the map. There was no sharp boundary where one clock suddenly changed by an hour. There was only longitude. Even solar time required refinement. The apparent motion of the sun is not perfectly uniform through the year, so well-regulated clocks increasingly followed mean solar time, an average day that could be divided into equal intervals. This is also where AM and PM come from. Ante-meridian, before the meridian, post-meridian, after the meridian. Noon is the meridian crossing itself. Local time worked well when life remained local. It became a problem when distant places needed to coordinate. Longitude was one of the great navigation problems. Latitude could be estimated from the height of the sun or the stars. Longitude required something more difficult, a comparison between local time and reference time. Imagine a navigator carrying an accurate clock set to the time at a known home meridian. At sea, the navigator determines local noon from the sun. If the reference clock says 2 in the afternoon when local noon occurs, the ship is 2 hours west of the reference meridian. 2 hours multiplied by 15 degrees per hour gives 30 degrees of longitude. The calculation is simple. Preserving accurate reference time on a moving ship was not. Temperature, humidity, motion, lubrication, and mechanical wear could alter a clock's rate. A small daily error could become a large position error during a long voyage. The marine chronometer transformed time into position. It did not tell the navigator where the ship was by itself. It preserved one half of the comparison, reference time. Local astronomical observation supplied the other half. Reference time minus local time became longitude. The same relationship would later reappear in electronic form. A GPS receiver does not begin with a map. It begins by comparing when signals were transmitted with when they arrived. Before the telegraph, a distant clock could not be compared instantly. A portable clock could carry time from one place to another, but the comparison took as long as the journey. The telegraph changed that. A master clock could close an electrical contact at a known instant. That event created a pulse in a wire. A distant chronograph could record it. A remote dial could respond to it. A railroad office, observatory, business, or subscriber could compare its local clock with a reference far away. Time had become a transmitted service. This did not mean every distant clock was physically driven by one master clock. Different systems used different methods. Some received periodic signals. Some compared local clocks and applied corrections. Some used telegraphic pulses for scientific measurements. But the conceptual change was enormous. For the first time, clocks separated by hundreds of miles could be compared almost immediately. Accuracy became visible across distance. And once clocks could be compared, their disagreement became harder to ignore. The telegraph did not create standard time. It created the network that made standardization practical. A town could live by local time. A railroad could not. A train crossed many longitudes in a single journey. It connected stations, crews, dispatchers, junctions, and other railroad companies. A railroad, therefore, needed an operating time that its employees would follow. One town clock might show local civic time. A railroad timetable might use the company's chosen operating standard. A connecting railroad might use another. The result was not simply one clock being wrong. It was several internally coherent systems that did not agree with one another. A railroad could solve part of the problem by synchronizing its own network. The Pennsylvania Railroad, for example, used telegraphic time distribution connected with the Allegheny Observatory. Its clocks could be internally coordinated even while civic clocks and other railroads followed different references. That internal order was not enough. At a junction, two railroads might bring different standards into the same physical place. A dispatcher could issue a train order based on one governing time. A crew could carry a watch set to that railroad standard. A timetable could specify a meet at a siding. Shared time was part of the operating authority. The danger was not that trains moved because a telegraph pulse controlled them remotely. They did not. The danger was that people making decisions about the same track could interpret time differently. By the early 1880s, the crisis was no longer keeping one railroad's clocks together. It was making separate railroad systems agree. Time was not invented by one person in one moment. It emerged from proposals, scientific coordination, railroad negotiation, and operational implementation. Charles F. Dowd proposed a North American system of hour-wide railroad zones. Sanford Fleming advocated broader international and universal time reform. Cleveland Abbey promoted scientific standardization so observations made in different locations could be compared. William F. Allen turned the problem into an operating plan the railroads could actually adopt. Allen consulted railroad officials and worked through the General Time Convention. His plan divided North American railway operations into 5 standards: intercolonial, eastern, central, mountain, and Pacific. The central meridians were separated by 15 degrees, corresponding to 1 hour of solar time. But these were not perfect geometric stripes imposed by nature. Railroads selected practical boundaries based on routes, cities, connections, commerce, and operating needs. The breakthrough was not discovering that 15 degrees equals 1 hour. The breakthrough was persuading independent companies to use the same framework. On October 11, 1883, railroad representatives approved the plan. The implementation date was set for November 18th. This was not yet a federal time law. It was a private operating agreement powerful enough to change the clocks of a continent. On November 18, 1883, the railroads changed time across a continent. But railroad agreement did not make standard time federal law, and it did not end the argument over what the clock should display. That is where Part 2 begins, with Congress, daylight saving time, and the continuing fight over who gets to move the clock. Subscribe to The Hidden Standard and continue with Part 2.